4 we start.
Alessandro ne approfitta del telelavoro lì in casa, sul sofà.
Hai visto? In realtà ero in ufficio pochi minuti fa. I was in the office a few minutes ago. I came home just to be comfortable to enjoy your lecture.
Okay. Ci vediamo dopo, no?
Sì, sì.
Ok.
Okay, guys, I think it's time to start. So welcome everyone to these invite lectures on the modeling and simulation for additive manufacturing. Today is a great pleasure to have with us Michele Chiumenti. He's extremely well established in the community of computational mechanics and in the community of additive manufacturing and simulations in additive manufacturing. So I will introduce him just briefly because, I mean, he's so well known. So Michele is a professor of continuum mechanics and structural analysis at the Department of Civil and Environmental Engineering at UPC in Barcelona since 2004. He's also professor at CIMNE, and his background is on nonlinear analysis, nonlinear constitutive equations, that he applied very successful to welding and in the last years to additive manufacturing. He comes from Italy, from Milano, but since his graduation he has been in Spain. So Michele, thank you very much really for your willingness to deliver this lecture, and we are very happy you're here and we look forward to your presentation. Thank you very much.
Thank you very much, Ferdinando, and all my friends here connected. Thank you, Massimo, for the organization. My presentation today is not that technical. I prefer to have just an overview of what we are doing, and particularly in 3 different lines where we are working or start working. One is additive manufacturing for metal. This is the more established one. But we are also working very much on additive manufacturing for polymers, plastic materials, and we are starting working with concrete. All our work is based on numerical methods. So let's say, as usual, CIMNE is not a reference on experimental labs, but we are a great center for numerical methods. So we try to do all the best for the numerical solution. Second thing that I would like to say is that what you are going to see is not all my work, obviously, but depends on the work of a larger team. I started working with my own group at CIMNE, where Miguel Cervera, Narjay Dailami, and Professor Carlos Agelet belong to. This is the COMET group. This is a serial software for finite element analysis and particularly thermomechanical analysis. But recently we moved to another platform, also developed here at CIMNE. This platform is FEMUS. It's a fully parallel platform for finite element analysis led by Joan Baiges and Ramon Codina. In the group, there are also people working on focusing on particle finite element method, and this is the group of Francisco Zarate and Eugenio Oñate. And finally, I would like to thank the group of GID, the GID group, which is, let's say, the pre and post processor that we are using for this kind of analysis. So, as I commented, the outline will go through three different kind of application of additive manufacturing, and I will show you the similarity of this technology in these three different fields. Even if the obviously materials are completely different, the industrial technology resembles somehow, and this is why we can use, let's say, the same platform for the three of them, but obviously there are some differences that I will show you. So I will start with the metallic alloy, then I will show you our work referring to polymers, in particular ABS, and finally I will show you what we are starting to do on concrete additive manufacturing. So the first idea, which I think is extremely important to understand, is that we are working on numerical methods, and numerical methods have some kind of limitation, and this limitation reflect the actual technology in additive manufacturing. I mean, in additive manufacturing, and if we refer to metals, there are three driving technology. The first one is wire feeding, and wire feeding typically work with very slow scanning speed, millimeter per second, and large thickness of each layer. Let's say from less than 1 millimeter, and right now, in this moment, we are working with aluminum component, and the thickness of layer is up to 4 millimeters. So quite large thickness and very slow deposition. On the other side, a lot of power needed for this kind of technology, and this means very much couple, thermomechanical coupling. In the middle, you can find blown powder processes. In this case, you have a heat source through laser or electron beam, and the melt pool, which is formed by this power source, is filled by powder, which is blown inside the melt pool. In this case, we are talking about layer thickness of about 200, 300 microns. So let's say 1 order of magnitude less than the wire, and the speed is ranging around 10 millimeters. So almost 1 order of magnitude more. Finally, and this is very much used in the industry, the so-called powder bed technology. Typically SLM is one of the technology. In this case, we are talking about 20, 30 microns, so 1 order less and 2 order less than wire. And we are talking about speed of 1,000 millimeter per second, so 1 meter per second, so completely different framework, thermomechanical framework. So the thickness is completely different, is very much more localized, the power is much less, and the penetration is much less. And another important thing is that in a powder bed, you have a recoating time, which uncouple more and more the simulation. So this given, in our opinion, the best way to, and probably the most reasonable and suitable numerical strategy for additive manufacturing is when you are able to perform a highly accurate solution of both temperature and the stress field. This means that you want to reproduce exactly, or the most exactly as possible, the actual industrial process. So you want to move as the heat source, and you want to follow exactly the same scanning sequence, and you want to wait for the same delay time as in the actual process. So at the end of the day, you end up with a fully coupled thermomechanical simulation, and I will show you which is the numerical solution for that. On the other side, on the other extreme, you have powder bed. In powder bed, it's almost, nowadays, it is almost impossible to think about in high fidelity simulation, meaning it is extremely difficult to follow the exact scanning sequence of the machine because the size of the layer, the thickness of the layer, and even the size of the melt pool is completely different, 2 orders of magnitude compared to the wire feeding. And at the end of the day, the simulation time will be impossible to manage. So typically in the market, the most used strategy consists of inherent strains or inherent shrinkage method to solve the problem in a layer by layer and typically lumped layer by lumped layer, meaning 10 layer by 10 layer simulation, which give you an approximate solution of the problem. Typically is not thermomechanical, but it's just mechanical simulation. And the objective is mainly distortion, meaning warp patch of the component. So it's a dimensional control for the fabrication, but you don't have any feedback on the temperature evolution, and even the stress analysis is very, very much approximated, as has been demonstrated, for instance, in the SIM-AM conference in 2018. So why high fidelity? We think that high fidelity is extremely necessary because if you don't have a solution in high fidelity, at the end of the day, you are just generating cartoons. So beautiful colors, wonderful for publication, but much less interesting from the industrial point of view. An example is the temperature field. Okay, in this figure here, on the left-hand side, you can see that with a small sensitivity analysis, we are able to represent exactly, almost exactly, the experimental result. Meaning, if you are able to calibrate the power source and you are able to calibrate the heat losses through convection and the radiation, as you can see here, the difference between the numerical result and the thermocouple is negligible. So you can obtain really a realistic solution. On the other side, on the right-hand side, you can see that if you just move from high fidelity to hatch by hatch simulation, not layer. If you do layer by layer, even worse. But if you just move to hatch by hatch, what you obtain is this kind of solution. This has been published a few years ago. But as you can see, you typically obtain the average evolution of the temperature, but you completely lose the peak temperature. And this means that typically you are not able to use this result as input for the microstructure modeling. And microstructure modeling means the quality of your component in terms of strength, in terms of microstructure, and later on strength. So if you just go from high fidelity to hatch by hatch, you lose this possibility. And exactly the same problem is encountered when you try to do stress analysis. So if you try to do stress analysis in a layer by layer manner, or even in a hatch by hatch manner, you lose the plastic deformation concentration induced by the source. So in my opinion, in our opinion, meaningless. So to do high fidelity, what you need? Well, first of all, you need a good framework, numerical framework. So what we did in the last less than couple of years, so after the SIM-AM conference, we moved completely all our development into a new software framework, which is called FEMUS, which is a Fortran 2008 object-oriented platform. It is based on OpenMPI. It allows you to run in both shared and distributed memory. We are using parameters for the graph partitioning, meaning for the subdomain division. We are using PEXI as a solver library, and we have a GitHub integration to allow the work of a larger team compared to what we had in Comet. So this is a very powerful platform, and we are actually running in very large machines. For instance, here in Barcelona, we have the BSC supercomputing center, where we can run the simulation in thousands of processors. So a large machine in distributed memory, typically distributed memory. Next, typically, as for many other industrial processes, the geometry is the bottleneck, and the meshing of this geometry is a nightmare. Apart from this, if you want to go in a high fidelity mode, you really need to follow exactly the scanning sequence, and this also means that you want to mesh according to the scanning sequence. So you want the definition of the mesh according to what is doing the machine. So you want your mem pool moving along the scanning sequence. So to do this, what we did is to integrate our solver to be able to read the same input data as the machine does. And this means our machine is able to read G-code. This G-code, for instance, can be generated through Cura, which is an open source able to generate G-code. And typically, the machine add to the original G-code, which is just a geometrical representation of the hatching, as you can see here in the lower part of this file, I put as an example. But in this file, you also have information, or is added information according to the processing of the process parameter of the machine. So, for instance, you have information about the power source, about the feeding rate, about the hatching, about the cooling time. So everything is inside this file. And it is the same file which is used to inform the machine, exactly the same. So this means that in our interface right now, we are able to import the G-code file as a representation of the scanning sequence. So you do not generate any mesh. The user is not asked to generate any mesh. The only thing that the user does is to modify or define the corresponding material database, typically temperature-dependent database. And the only thing that the user is required to do is to define the number of uniform refinement level and octary refinement level to approximate this geometry. And I will show you right now. We do not have any mesh at the beginning of the process. We just have the part represented through lines coming from the G-code. So the first step is to define the so-called bounding box. So you just have one finite element. This is this finite element is the bounding box of the component. Next step is to define a number. Typically, we are using about 4 uniform refinement, and this generates a uniform Cartesian mesh of the component. Next, there is a following step in which you have the so-called octary-based refinement. The octary refinement just split one element into 8 elements, and so in different steps. Okay, so at the end of the day, in the lower row here, you can see how you have a very large element where the mesh is not needed, and you have a very fine mesh where you really need to represent your component, and you are exactly following the scanning system of the machine. Obviously, all the elements outside the zone where there is no material are not used, are not ensembled, are not computed, nothing, are just there, but are completely out of the solution scheme. Next, reading the G-code, we are able to define a bounding box for each part of the hatch, which is defining the G-code. This is typically a bounding box like this, which take into account on the layer thickness and the width of the spot size. and we intersect this volume with the surrounding mesh. And this process is done in parallel, so each processor is doing exactly the same operation and defining which are the elements to be activated. And if the background mesh is too large to represent this bounding box, the mesh can be further refined up to the situation in which we are sure that we have a good representation of the mesh for this kind of bounding box. So here in the second row, you can see how the mesh is generated and how the automatic mesh refinement takes place. In particular, you have a refinement in the heat affected zone, and then you have a coarsening operation elsewhere else. So at the end of the day, this is the kind of simulation that we can do. So as you can see, you have a mesh which is progressively built according to the scanning sequence, and at the same time you have the solution of the problem. So here I'm just representing the active element. So all the other elements are not active and are not computed and are not visualized in this process. Here you can see that for the part that I showed you just before, we are using 4 levels of uniform refinement and 4 levels of octave refinement. Next, I will skip most of the detail of the thermomechanical formulation because you can find these details in our publication. And apart from this, we are just enhancing every day our background formulation. But I just want to insist on a couple of things. First, if you are working at the level of single track, it is interesting to define the laser beam input as a Goldach distribution, meaning to a double ellipsoid power source. And we have this facility in the software. And this is worth if your time step is small enough compared to the size of the spot. This can be done, and we have very nice result. And in fact, this is a specific kind of framework where we typically look at the microstructure. We look at what is going on at the melting pool level. But if we are talking about component scale, you are not moving along the scanning sequence in using this so small time step. So you are typically moving from this position to this position, and this means that at the end of the day, in the time step, you are applying the power in a much more larger domain, and this means that you are integrating the double ellipsoid through the time steps. So let's say it is an averaging. But still high fidelity, meaning you are still moving very slow compared to the size of the arch. Next observation, constitutive modeling. We are working on a more accurate constitutive model at the moment, but just to clarify a bit, all the material properties are temperature dependent. This is key point, and particularly it's important to consider the yield stress as thermal dependent parameter. Something that was, at least for me, new, if I can say, is that our model behaves differently when the material can be assumed as solid and when the material is assumed as mushy or liquid. Typically, when the material is solid, we have a viscoelastic, viscoplastic model. And this means that you have elasticity. Well, here you can see the elasticity term and the viscosity term. But what is more important, you have a viscoplastic behavior. So you have this damper in parallel with the plasticity. And what happens? And that when you switch to the mushy or liquid phase, you want to represent your material as a liquid, as a viscous liquid. And typically what you want is to represent it through a purely Norton-off model. So from the on the volumetric side, you have just thermal deformation, but on the deviatoric part of the stressor are represented just by a damper. Typically, it is a non-linear Norton-off, which behave as a rigid viscoplastic material. So now, the transition between solid and mushy behavior, typically, in my publication, I was putting the solid fraction as a transformation parameter able to switch from one to the other. But we noticed in the last year that the key parameter to move from solid to liquid behavior is the annealing temperature. So just to have an idea, the liquidus temperature of titanium, it's about 1,600 degrees, while the annealing temperature for the transformation of the constant equation go at the 900 degrees, so almost half of the temperature. So this means that we are considering a viscoelastic, viscoplastic model till the annealing temperature, and then we move to this viscous model. The thermomechanical coupling is solved through a staggered solution. So typically we solve the thermal problem and then we go through the mechanical simulation in a staggered way, so quite classical. I must say that the coupling is quite weak coupling, meaning that the mechanical problem is completely affected by the thermal field, but not the reverse. Finally, we are working, and we just this week I just could see the first result, very interesting result on the finite element technology. First items. If you use just standard displacement-based formulation, this element is inaccurate and it's unable to deal with isochoric constraints. This is important. To be able to play with incompressibility is extremely important in additive manufacturing. Why? First, because when you are liquid, all the deformation are purely deviatoric deformation, so isochoric deformation. But also when you are solid, all the plastic deformation come from a J2 plastic model. So also in this case are isochoric deformation. So it is extremely important to consider an element able to deal with the isochoric constraint. So the classical solution for that is a displacement pressure or velocity pressure element. So we have this element fully understood, implemented in different situations, both for solid and liquid analysis. Typically, we use orthogonal subgrid scale stabilization to play with linear field for pressure and velocity or displacement. But this element, okay, it works for incompressibility, but is still somehow inaccurate. So it is still a linear element. So if you want to do something better, particularly close to the eta theta zone or in the eta theta zone, we have the possibility to switch to a more accurate element, and this is the case of a three-field formulation. This is a displacement, deviatoric strains, pressure element. So you have the three field at each one of the nodes, and you have a linear interpolation for each one of them. To deal with the Babuzza-Brezzi constraints, once again, we are using orthogonal subgrid scale stabilization. Okay. So first of all, we demonstrate in different publications that this three-field formulation for the same number of the degree of freedom is more accurate than linear elements, meaning that you could refine the mesh, having a very fine mesh using linear element, and you spend the same if you use a three-field formulation. So it's a very powerful element, but this element is fully compatible with the UP formulation, meaning the pressure and the displacement field are the same at the two sides of the mesh. So This is the case of the melt pool, for instance, or the Ita-Feteson, where you have the largest gradient. You can use the three-field formulation where necessary, so where you have large gradients, and then you can switch automatically to the UP formulation in any other place. So an example here is here in these figures where you can see what I presented also for friction stir welding. This is a simulation where you have a very strong gradient close to the pin. And here you can see what you can obtain using UP formulation and what you can obtain using the three-field formulation. So completely different accuracy. So at the moment, our solver allows to use both formulation at the same time. And the idea is to fix all the degree of freedom of the deviatoric strains when they are not necessary. So at the end of the day, we have a NOC3-based finite element refinement for the, let's say, the H refinement, and for the P refinement, somehow it's not P, but okay, formulation refinement through this three-field formulation. Now I will show you something, 34, okay. I will show you something about additive manufacturing for polymers. In this case, the first things is to understand, or what we understood is that in this case, the main objective is not processing, it's performance.
Michele,
so in this case, we are not going to simulate the processing, the building of the part, but what is the interest is in the performance of this component. And why? Because typically these components are made by filament, fused FFF, fused filament fabrication. And so the material behavior is not isotropic at all. So here you can see, once again, the different technology in the market. On one side, you have the fused filament fabrication, which is our objective at the moment. Typically from Stratasys, Ultimaker, Barcelona 3D, for instance, here we have a large company working on that. This build the part through filament, but there are also the SLS. So in this case is powder bed, as in case of metal. And the third possibility is through multi-jet fusion, okay? This is a selective sintering of the material and some ultraviolet light. Now, how do we work? Which is our strategy in this case? So once again, we use G-code. The G-code represents exactly the scanning sequence, well, the deposition sequence to deposit the filaments. Once we have this, we go through a voxelization, and after the voxelization of the full component, after the voxelization, we go through an OC3-based coarsening. So at the end of the day, we have a mesh very well optimized, where you have the element where necessary, and all the rest use a very coarse mesh. Next, we need to define the material data for each one of the zone of the component. And as you can see in these figures, during the printing process, typically you have three kinds of printing setup. The first one is the one on the skin. Typically, these are aligned filaments, completely aligned filament, which follow the boundary of the component. Then you have what we call covers, typically the bottom and the top covers, which use a crossed filament. It is 100% infill with 45% and minus 45% crossing. And finally, you have the infill. This can be just infill like the one you can see here, or can be done through lattice structure. So once again, you don't want to simulate this lattice structure as it is, micro modeling, but you want to do some homogenization. So at the end of the day, you need to characterize external contour, covers, and infill structure. So to do this, what we did, we have been involved in different local Spanish projects where we had the possibility to characterize the materials. At the end of the day, we generate specimen with aligned filament as the one on the top, and the cross filament, 100% infill, 45 minus 45, and using different printing orientation, we were able to characterize the constitutive tensor. Observe that typically what you obtain at the end of this work is a fully orthotropic tensor of the material. You can simplify a bit without loss of accuracy as a transversal isotropic material, but still not isotropic. Next step is to define the behavior of the lattice structure. Well, in this case, you have lattice structure or infill structure. At the moment, we were working with infill structure. So typically 45, minus 45 rasters. So what's the solution? The solution is to go from the actual lattice structure to one homogenization of this lattice structure. And the result is once again an isotropic constitutive tensor. So here we are using periodic boundary condition, and we are obtaining the constitutive tensor for this material. Once you have the homogenization of the lattice structure and you have the material characterization of the contour, we went through a different demonstrator to validate our software. So I just show you one of them that we did with the help of Eurecat. This is a door handle demonstrator, and it is being printed in 3 different orientations and loaded. Observe that this is a quite difficult test, in fact, because it includes both bending and torsion tests. Well, this is the result once terminated the sensitivity analysis. We did the work using the 25% infill and 2 skin for the layers, and the second kind of specimen were built using 50% infill and also 2 skin for the layer. In the paper, you can find other combination. But at the end of the day, what is the result is that the model is able to predict the stiffness of this material in all the different orientation. Finally, I would like to conclude my talk with some recent approach to additive manufacturing from concrete. This is very young, and we probably enter into this world by the beginning of September. In additive manufacturing for concrete, there are also 2 kinds of technology, very similar, once again, to the ones in metallic alloy or plastic alloy. One is contour crafting, and the other one is powder bed technology, what is called D-shape. Well, the contour crafting is very similar to what we were used in wire feeding. In this case, you have an extruder, which is extruding the material according to a specific scanning sequence, or in this case, deposition sequence. So you have a robotic arm able to generate a different layer of material according to a specific sequence. And they have exactly the same problem as for metallic alloy. When deposit, which is the timing for this deposition, in case of metallic alloy, the problem was temperature. Here, the problem is the hardening of the lower layers. So this is the first technology and has been used to build interesting stuff. So for instance, we have the first residential 3D printed building in Europe and big machine to perform this. And the future could be even the possibility to build construction on the moon or in Mars or whatever you want. The second technology is D-shape. This is a specific technology very much developed by Acciona here in Spain. Acciona is a very large company in Spain, and they are investing very much on this technology. As you can see, it is a powder bed technology. So once again, similar to the one for metal or for plastic. In this case, you are selectively wetting the powder, the concrete, and they are using one kind of binder. And once the material solidifies in a layer by layer manner, at the end of the process, they remove the loose powder, and you can obtain the final structure. So it is quite different technology from the previous one, and the numerical tool should follow a different criteria. Note that in Acciona they have a machine which is, let's say, 5 meters by 2, but in the Arabic country, they are using a machine of the size of a tennis court, so quite big machine. The result are structured like this, and for instance, the first one on the top is a bridge that you can find in Madrid. Okay, but you can print different structure and with very complex geometries, and the future can be also sculpture or architectural application. So very nice and very complex structures. So you can have the same facility that you can find in metals can be obtained through concrete printing. Now, constructive model. We have a previous expertise and experience in young behavior of concrete because we use this kind of constructive modeling for dam construction. Okay, so typically the model is more complex, meaning that you have to couple not only the thermal problem, but also the chemical. You have a chemical problem. So you want to go through hydration, aging, and you can have problem of cracking and creep. So not only thermal deformation, but also the effect of the water content. At the end of the day, the model that we typically used at that time was a viscoelastic damage model. Most of the work is done on the viscoelastic behavior of the material. Typically, we're using chain of dampers and stiffener, and you typically have an aging filled surface. What you typically need to get from the experiment are curves like this one, where you can see how the strength is increasing with time and how the stiffness is increasing with time. So this will be the main input for the software. So instead of having a temperature dependency, you have a time dependencies according to the aging of the material. So at the end of the day, we would like to use exactly the same structure that we have for framework, that we have for metallic alloy, and which is always also the same that is used to generate the mesh for polymer material, also for concrete based additive manufacturing. So we can once again follow the position of the position sequence of the concrete and just plug in a new rheological model for this kind of material. Observe that typically these materials are not just concrete as usual concrete for civil engineering construction, but at the moment we are in touch with Acciona, with Aramco and other companies, where the objective is to use even 30% of polymer material into the mixture of this concrete past. So it is really a new material that must be studied. So conclusion, we are very much interested in defining a framework for the numerical simulation of additive manufacturing. The material itself is not the key point, meaning that we would like, the objective right now is to have a good platform for all materials, and then each specific application will use its own constituted rheological model. We still think that high fidelity is fundamental. So we do not want to do a layer by layer activation. We don't want to reduce the model that way, but we would like to do as much accurate as possible, meaning following the actual scanning sequence of the machine. And for this reason, we decide to move to G-code, the driven geometry. To do high performance simulation, we need good parallel framework, and we demonstrated weak and strong scalability in our publication. To keep under control the number of finite elements, meaning the requirement of the machine, we have a very powerful octave-based adaptive mesh refinement technology, which keep the number of elements almost controlled during the full construction. And depending on the material, we can play with viscoelastic, viscoplastic material, north and off in the mushy zone. And as I showed you before, in case of concrete, we are playing with the viscoelastic damage constitutive model. According to the finite element technology, we think that it's mandatory to have a technology able to deal with isochoric problem, meaning at least UP is the minimum requirement, or B bar element in case of hexahedral elements. But if you want to increase this accuracy, even locally, we can use the three-field formulation. And in this sense, we publish a couple of papers showing the benefit of the three-field formulation. Well, here I also added the metallurgical solution. I had no time to explain to you what we did on the metallurgical side, but we are also moving forward in this direction. So I would like to acknowledge some of our partners in some of the projects that we had. At the moment, the module for metal alloy is being supported by ArcelorMittal. So ArcelorMittal is our main sponsor, while Acciona is our main sponsor for the concrete work. You can find in my webpage all the references concerning to additive manufacturing, but also with the finite element technology. So both UP and three-field formulation are uploaded in my own webpage. So I would like to thank once again for to participate in this seminar, and I hope to see you face to face, probably in October, or when the situation will be some better after the beginning of the courses at least. But I will be very glad to meet you and to have a feedback on your side and possible collaboration in projects and further development of the software. Thank you very much.
Michele, thank you very much. Really appreciated the concise but extremely broad at the same time presentation. Since I think all the audience is working in the area, we could really appreciate the effort and the results that you were showing. Really impressive. So thank you very much.
The one that you are seeing here is just a stupid simulation, but is what Eugenio Oñate and Francisco Sarati are doing, switching from discrete element, as you can see, powder, finite element. So when the material consolidate, transform into a finite element approximation. So this reduces the number of degree of freedom of the powder to transform into something which is represented through finite elements and which can use the constant equation of finite elements, which are completely different from the ones of particles. So I apologize that I cannot enter into the details of all this stuff. There are too many. It was just an overview of what we can afford, and what we can. You can just get in touch with me, or you can have.
Well, we invite you. We already reserve your time for another seminar where maybe you explain these other details, because that's something I didn't. So it's really interesting, this switching. So let's open now the seminar, the presentation for questions and discussion. I have several, but I would like to first ask the audience if there are comments, questions. If not, I mean, you can raise your hands and then you can start asking questions. Otherwise, I will start with the one question. One question is relative to the annealing temperature. You mentioned the importance of the annealing temperature, on which I completely agree. Clearly, you use this annealing temperature only when you model the phase transformation from liquid to solid steps, right? Not from powder to liquid, or you use the same annealing.
No, this is to switch from the constitutive model used for solid to the constitutive model used to represent something which is mushy or liquid. This does not mean the material is liquid, because in fact the liquid temperature is 1600, but This temperature is typically, in titanium, for instance, is the phase transformation from alpha to beta. But what happens is that the material can be assumed as a solid or behave as a solid till the annealing temperature. After this temperature can be represented through this viscous model. Obviously, is a nonlinear Nortonov model, so is a non-Newtonian model.
Yeah, but do you do these? I mean, is this temperature? I mean, use this temperature both during the increasing of the temperature and the reducing of the temperature, or only in one direction?
At the moment, we are using in both directions.
Okay, okay. And you think it's I mean, that's the right thing to do, or you think it could be better to use a different temperature when you increase it and when you reduce the temperature?
You can probably use different temperature, and you can probably consider different. As far as I know, also even the thermal expansion coefficient is not univocal, meaning in both directions. So there is still possible to
improve it a
enhance the
little.
model. But the key question is to be able to remove the stresses, typically the deviatoric stresses, because we dissipate through viscosity when you reach the annealing temperature. So this makes a sort of reset of the deviatoric stress. And this is key. If you don't do this, you typically see peaks, spurious peaks in the displacement curve and in the stress curve.
No, I agree. Okay, thank you. Let me ask you another thing, because that's probably my I didn't pay attention, but to the literature. But you were talking about this mixed displacement strain pressure approach with the subgrid stabilization. Which functional formulation do you use? So it's not a Uva-Shizu, it's an ad hoc formulation that you develop in order to develop.
No, the starting is still Uva-Shizu formulation.
Okay.
It is, apart from the stabilization, we make things more complex and couple the original formulation just using the three equations, one for the balance of momentum equation, one for the kinematic equation, and one for the constitutive equation, make very natural the use of the three-field formulation. And the split into volumetric and deviatoric part make very natural and efficient for isochoric problem. So just include both the benefit of having the pressure as main variable, and also the deviatoric strains to deal with to increase the accuracy. Having continuous strains make the accuracy increase 10 times with respect to the standard element. So it is really powerful element. Obviously, it is more expensive, but as I said, right now we have an implementation so that you can selectively activate the degree of freedom of the deformation where needed. So just around the melt pool, just to say. So at the end of the day, it increases very much the accuracy, and the cost of this is very low.
Okay, thank you very much. So there is a question from Damien Toure. Please, Damien.
Hi, good afternoon. Yeah, I'm Damien Toure at Imdea Materials in Madrid. Well, thanks a lot first for the impressive talk, very interesting. And I was glad to learn we have a 3D printed bridge here in Madrid. I didn't know. Now I have it on my list of things that I need to visit urgently. So my question was going back to phase transformation and temperature dependence of the properties. And more specifically, how do you deal with like evaporation? So, if you don't take that into account, from my understanding, if you don't, with the laser, the power source that you have, you reach peak temperatures that are, way above the evaporation temperature. How do you deal with that with the simulations?
In the simulation, we do not take into account the evaporation itself. What is typically done is that you have an efficiency parameter, which is applied to the power source, which takes into account the evaporation. So typically, if your input is 300 watt, you will use 65% of this power, because part of it is lost through radiation or evaporation or what's happening in the process. So this is one of the parameters to be very accurately defined. Observe that in case of wire feeding, our efficiency parameter, it is around 0.75, 0.80. Using blown powder, the range is 20% or less. So most of the energy is either reflected by the powder, by the shape of the powder, and or other stuff that I really do not know, because I'm not an expert in material science. But what is coming from the experiment, and I was in China at the Northwestern University to do all this experiment during the long time, but it was very clear that most of the power was lost. In case of SLM, you have also a quite big amount of energy losses, less than on blown powder, but still very remarkable. But as I said, from our point of view, meaning when we look at the component scale, for us is just a parameter to be defined. And as you could see in the simulation of the temperature, you can really achieve very high accuracy. Here you can see. So absolutely. If your objective is the melt pool, probably what you said is extremely important, and this is key in this kind of simulation. But when you look at the component level, much less.
Okay, thank you very much.
Okay.
If there is time, I have a question also.
I was waiting for you, Massimo. I was surprised. Go ahead, please.
So you say that you are looking at the component scale, but at the same time, you aim at high accuracy, especially in the stresses with this three-field formulation. Now, you do this simulation for the stresses with this octree adaptivity. So locally, you can be very accurate, but why do you need this accuracy at that local scale if at the end of the day, you will coarsen a lot in the part scale simulation at the end? So the resolution of your stresses far away from the melt pool will be not so accurate, at least in H.
Very good question. I have two answers for you. First, in my personal opinion, well, I give you for the first answer, then I give you the second, my point of view. The first answer is that we just wrote a paper published in 2020. The first author is Joan Bages, which is the leader of the octree stuff, where we explain how to retain the accuracy of the octree when you do coarsening. And obviously, you are right. When you are doing a coarsening, you are losing something. But what we did is to consider an extra term, let's say a correction term, to be placed into the coarse mesh to retain the same kind of distortion as in the fine mesh. It's not so easy to understand.
No, but I know
the idea is to retain the deformability of the fine mesh into the coarse mesh, and to do this, we are doing an equilibrium of the two discretization, and we are generating an extra term which is plugged into this element. So you are completely right, but using this extra term, we saw that this is working. Now, to what we did now, this worked very well when you go from fine mesh to coarse mesh. So when you are coarsening, and it worked very well, and it retains the solution. Now, if you go back once again and you remelt once again, and so you have to refine the mesh once again and then coarsen once again, this is much more tricky. And so we are still not able to do this cycling change of the mesh. So at the moment, our solution when we deal with this kind of problems is to use the fine mesh till the laser is working in this zone through the depth of through the penetration, let's say, of the laser, where you have an effect on the plasticity. Just to say, for instance, in case of SLN, we are talking about 3-4 layers, okay, something like this, and then you go through coarsening. So in the publication that you can find in my webpage, you can see a component made by Additive Manufacturing where you have a level of very fine mesh which is moving through in the theta direction, and which is used in the thermomechanical affected zone, and below this you go through coarsening. But you need to add this term. If you don't add this term, as I think most of the commercial software does, the solution is wrong. Is wrong, and we demonstrate it. So you really need to do something, and you are completely right. Now, the second answer is, in my opinion, if you have to really deal with a big component, it's not that easy. And so we are also thinking to a solution which is based on zones. So you want to split the part in a different zone of interest for the industry, typically coming from the thermal solution, where you can see that you have some thermal concentration, whatever, and in this zone you can apply the stress analysis. So probably is not that worth to do stress analysis in every place. First of all, because it's extremely expensive, and secondly, because it is not that necessary. But right now, what is clear is that industry is very much interested in the temperature field, but they want to see the actual temperature field, meaning including the peak temperature, because they want to plug in the metallurgical modeling. And this is extremely important because from the metallurgical model, they can obtain the microstructure and then the strength of the material and whatever. So the production will be optimized through the temperature field. Now, and this is important. We are not expert in metallurgy, so we are not the best solution. We just have approximate solution. We have a couple of papers published on that. But it's always possible to plug in the work of other very expert guys, like the one in Aachen from Access, for instance, where they can just take as an input our temperature and then can play with their automata modeling to get microstructure as good as you want. On the other side, so from the temperature, for the accurate temperature field, you can obtain metallurgy from these material properties, and from the mechanical side, what you want is to retain the accuracy of this fine mesh into the course, and this is why we have this correction term. So I suggest you to have a look to this paper, and then we can discuss it, and you will see. But it's not difficult.
But I know the paper of Baiges, and the question exactly was this. Your second answer was perfect for what I had in mind. This the problem.
Yes. You have to separate. Yeah.
You have to separate the zone and like zoom into specific problem for the thermomechanical.
For instance, you can do layer by layer or whatever you want up to a certain level, and then activate the high fidelity as more accurate as possible.
Yeah.
And you will have all the deformation, all the stresses, everything.
Yeah,
so
because
you will activate the zoom where needed. Yeah.
Because you always kept in that article cluster of layers. So in that sense, it's an agglomerated. It's not agglomerated because you follow the laser, but from an adaptivity point of view, it's kind of agglomerated.
Yeah.
Okay. Yeah. Thank you. Thank you very much. It was really enlightening.
We have to be engineers somehow, because we cannot go with brute force all the time, and we have to think a little bit. And I think it's very important, the relationship with enterprises, to really know what they are looking for and what they are going to optimize and to work with. For instance, at the moment, as far as I know, enterprises really are interested in additive manufacturing, but because of the low productivity of additive manufacturing like it is now, they are using multi-laser, not only in SLM, which is well known, but they're using this for wire. And they are using, at the moment, our enterprise is using 4 laser to do wire feeding. And so they are able to build big components with a very large number of laser working on the same component, but for this, they need to optimize the temperature field, the distortion, everything. So there is a lot of work on optimization of all this, particularly from the thermal point of view. But the future will be the use of multiple laser on the same component working.
But why is sorry, I'm taking maybe too much time. Stop me in case.
Don't worry.
You say that now, in your opinion, the highest interest is the peak temperature because it has a connection with the metallurgy of the part. Of course, that is true. The cooling rate affects this, but also the global temperature of the activation of that layer plays a key role. And maybe we are not too much interested in what occurs at the very local region around the melt pool, because at the end of the day, that part is almost steady state for a large part of the process. Instead, the activation temperature really change the material microstructure from one part to another. For example, I'm thinking about lattice structure where you see martensitic region on the skin and a larger cell in the microstructure inside. And this is due to the residual heat that you have. That depends on the layer effect and not too much on the local.
There are two, I'm not an expert on metallurgy, but we have here a Chinese guy working in, behind this guy, there is the Xi'an University. And so he is doing all the experiment to check the metallurgy and particularly using DOD technology. And we implemented a simplified metallurgical model that you can also find in my publication. It is quite nice publication because just from an engineering point of view, show you which are the key factor in the metallurgy. And there are, just to let you understand, there are two key points. One is the cooling rate, as you said, first during the activation. So you need to reach the peak temperature, but then the final cooling rate, because this final cooling rate, once you go through the alpha beta range, this cooling rate will define the final microstructure in terms of alpha phase, beta phase, or martensitic phase. So according to this speed, this rate, you have one microstructure or one other. So you need the accurate definition of cooling rate. Second, and probably more important, each time you go through the alpha beta phase, so each time you go through this range of temperature, you have a sort of coarsening of the grains, of the lamellar space. And this generates you have a coarsening of the microstructure. So each time you have this kind of cooking, I call it cooking time, more time you stay in this alpha beta range, the larger is the microstructure. And at the end, the lower is the strength of the material. So they did a lot of hardness impact to compute the hardness experiment, to compute the hardness, and they compare to the microstructure evolution, and they also relate this to this cooking time, so the time spent in this alpha beta period, and the correlation is quite good. Not that much in SLM, because in that case, the cooling rates are too fast and typically you obtain martensite. But if you work with wire feeding or blown powder, this works quite well. So at the end of the day, you need a good temperature field, you need an accurate definition of the temperature to see the time that the material spent in the alpha beta range, and this will give you an idea at least an engineering idea at my level, at least, of the material properties. So I think this is good, and this is the interest on the thermal analysis and the accurateness of this thermal analysis.
Okay, thank you very much. That was a really nice explanation of the problem. So you need both these two levels together to get an idea, an engineering idea of what is going on. Thank you.
Okay, I think it's now is 5:15, so clearly there are many due to the subject, there are many open points and possible further discussion, but I think it's good that we close here and we can be in touch in any case. And Michele, thank you again very much for the concise but extremely deep and enlightening presentation. So thank you again, and we look forward for your next seminar in our series. And we also look forward really to meet all together as soon as possible.
But
so
this
thank
time
you.
I need a restaurant.
Absolutely.
I must be paid with some kind of good food.
I completely agree on this. I am very disappointed. The few times I give a web seminar is always very disappointing because we miss that part. So I swear with my right hand.
I remember a good restaurant in Pavia and still remember a good risotto in Pavia. So
I will take care of this. It's my responsibility. Don't worry.
Grazie ancora, Ferdinando.
Grazie molto a te.